So, Chapter 5, things you should know for your Unit 2 exam. One of the things we talked about in Chapter 5 was that group of energies called electromagnetic radiation, and I kind of called them cousins. So you need to kind of know them in order of course, this is highest energy gamma rays down to lowest energy radio waves. And smack dab kind of in the middle there is visible light, and you kind of see me, how I've used the acronym ROY-G-BIV going backwards for visible light. So know that. The next terms kind of go together. Frequency, with regard to frequency, what frequency is basically the number of waves that pass a certain point in 1 second. So cycles per second we call hertz. And so in green here you can see above gamma rays I've put the highest frequency. So basically, actually it's the shortest wavelength and the highest frequency associated with that in most energetic form of electromagnetic radiation. So they're very small. These are all traveling, by the way, at the speed of light. So also with regard to speed of light, remember that there is a relationship, an important relationship between, for any given energy, that energy's frequency and wavelength. If you multiply for that given energy, the frequency times the wavelength, you get the speed of light. Okay. So just one thing that's important, remember we said that with regard to these different forms of electromagnetic radiation, we said gamma rays have the shortest wavelength and radio waves have the longest wavelength. Okay, next topic there, structure of an atom. So we need to just basically talk about 3 subatomic particles: protons, neutrons, and electrons. And if you've seen up there in the upper left-hand corner, I've drawn that circle represents the nucleus. Inside the nucleus, of course, we have the protons and the neutrons, and then we have the electrons in a cloud outside the nucleus for any given atom. And then related to that, a couple of terms you need to know. Atomic mass number, I kind of highlighted in blue up there. Atomic mass number is the number of protons plus the number of neutrons in the nucleus of an atom. So that actually kind of it's what gives an atom its mass or its weight. But atomic mass number is going to be a whole number, an integer, because you're really counting particles. The atomic number then is actually just the number of protons. And the atomic number, the number of protons, is very important because the number of protons, the nucleus of an atom, identifies what element that atom is. The next topic there, we said that light or different forms of electromagnetic radiation will interact with matter, and it depends upon what the matter is, and it depends upon what the energy is. But there are 3 different things that can happen. That energy can be transmitted by the matter, so the matter doesn't care it's there, the light just goes right through. That energy can be absorbed by the matter. Or that energy, once it hits that matter, can be reflected or scattered. Okay, 3 types of spectra, and I went ahead and brought in a photo from the internet to kind of highlight the 3 types of spectra. So the top spectra, I know it says continuum spectra, but actually it's what we call the continuous spectra, which is Kirchhoff's first law. But the continuous spectrum has no lines, and actually it's what we use to create these black body radiation curves. These curves then can actually tell the temperature of objects. Okay, no lines though. The next type of spectra, Kirchhoff's second law, actually is what we call an emission line spectra or a bright line spectra. And what's happening there, and this is the second term or the following term on your review sheet, what's happening to create these lines is that excited electrons are falling back down and emitting this energy. And then the last, Kirchhoff's third law down there, are the absorption line spectra or dark line spectra. And what's happening there is that, again, it has to do with the electrons. Electrons are actually being excited up to an excited energy level, and to do that they are robbing energies at those wavelengths and creating those dark lines. Okay. The next topic there are 2 types of telescopes. So the 2 types of telescopes are reflecting telescope and refracting telescope. So reflecting telescopes use mirrors, refracting telescopes use lenses. Then I also have a term focal point, and so I'm kind of laughing because you're going to see me draw 2 telescopes down here. Um, the excuse me, the focal point basically for both types of telescope is where the light it comes to a point. So that first telescope I've drawn, I don't know if you can tell it, but we have light coming down the tube, and at the back of the tube, telescope tube actually is a mirror. So this is a reflecting telescope, and that green dot is where light is gathered to a focal point. And then, of course, the other type of telescope is a refracting telescope. Refracting telescope uses lenses, and so I'm kind of showing you the light is being gathered to a point. Again, that green point is the focal point of that telescope. Angular resolution in general is just telling one characteristic of the telescope, its ability to resolve fine detail. Then we talked about red shift, blue shift, one shift, two shift. No. The red shift actually is created as a source is moving away from the observer. And if you're looking at spectral lines, then what's going to happen is spectral lines are actually going to be linked. You're going to see your spectral lines that are going to be created, either emission or absorption lines, but these lines are going to be shifted to longer wavelengths of light, i.e. a larger nanometer, okay, if you're reading the data. Blue shift then is where a source is moving toward the observer, and then in this case, if you're looking at spectra, you're going to see these lines are going to be shifted to the shorter wavelengths. Okay, so on to chapter. Oops, sorry, one more thing. Why do we put telescopes in outer space like the Hubble Space Telescope? And then up there in purple, in the upper right-hand corner, you see 1, 2, 3 reasons that we would tend to put, it'd be advantageous for us to go ahead and have a telescope orbit the Earth. Notice one of them is not to get closer to the star. Okay, that's like really, we're not getting anywhere, anything really appreciable closer to the star. But what we are able to do then is to get away from light pollution on Earth. We're able to get away from the Earth's atmosphere that creates turbulence for land-based telescopes. And we're also able to go ahead and get to some of those energies that are absorbed or blocked by the Earth's atmosphere. Now on to the next chapter. So solar nebula in general, we're talking about the early on stages of our solar system, basically that blob that ultimately became our sun and the planets. That's the solar nebula. We talked about 3 different ingredients in the solar system, in the solar nebula, and in order of their abundance, I have them listed here. So we said, I listed the 2 in green first because they were most abundant. What our solar nebula that created the sun and the planets mostly was made up of, and that matter was conserved in what we have today, is hydrogen and helium, okay, followed by hydrogen-containing compounds. So by far, that's the lion's share of the abundance of the stuff in the solar nebula. So 3 and 4, the last 2 things with regard to stuff in the solar nebula that formed our solar system were rocks and metals, by far in minor amounts. The solar nebula, that blob that ultimately became our solar system, when it began collapsing, okay, it had a little bit of rotation, and that rotation had to be conserved in the smaller footprint. And so just like when a skater brings her arms or his arms in, he spins faster and faster, so also did our solar system. And the other thing is we basically converted some of our potential gravitational potential energy to thermal energy. So we spun faster and we got hotter. I went ahead and brought in a cute little diagram here for the next one. Okay, I think this is adorable. This is a figure from your textbook, and we see kind of the budding sun, kind of a protostar in the middle of the blob there, and then we know that via accretion the planets formed in kind of tracks outside the sun. And then if you take one of those planets that's forming, actually that's supposed to represent Jupiter there on the right, it actually kind of has its own little disk of material that formed its own little set of moons in orbit about Jupiter. It's adorable. The next one, anomalies of our solar system that needed to be explained when we come up with when we have come up with the nebular theory, the formation of our solar system. One is Earth's large moon, okay, kind of uncharacteristic of a terrestrial planet like the Earth to have a beautiful spherical large moon. And the other thing is Uranus. Remember that that blue gaseous giant, when it rotates on its axis, actually its axis of rotation basically lies in the plane of the ecliptic. And both of these kind of anomalies or odd things about the objects now in our solar system can be explained by kind of a period of lots of roving extra stuff, kind of potentially bombarding the Earth and potentially bombarding Uranus. Okay, so the two types of planets, of course, we have terrestrial planets and Jovian planets, and I want you to be able to say kind of how they're different. So I put small and large, rocky and gaseous, inner and outer, with regard to terrestrial and Jovian planets. Origins of Earth's water. Actually, we think Earth got its water early on when there was material kind of roving the solar system. So things were crossing what we call the frost line, coming this way and that way of the frost line. And so we basically had icy bodies that brought and deposited water on our budding planet. It's kind of fun, isn't it? So here on the review sheet, I kind of limit accretion to terrestrial planets, but really it doesn't have to be rocky bodies. Accretion basically, in terms of the formation of objects in our solar system, is just matter that is gathering together. And I kind of likened it to creating a snowball out of snow. Okay, so that's accretion in general. The frost line then is the temperature, or the demarcation of two zones. The warm zone and the cooler zone, the hot zone or the cold zone, if you want to call it that way. And what the significance there is, on the warm side of the frost line, only rocks and metals could go ahead and come out of their gaseous state. And so that's actually where we got our rocky terrestrial planets. And on the far side of the frost line, on the cold side of the frost line, it was cold enough that not only did rocks and metals go ahead and come out of their gaseous phase, but also so did those compounds, those hydrogen-containing compounds. So then in a nutshell, the frost line kind of marks where we have our inner terrestrial planets and our outer gaseous planets. So the last term there, I went ahead and brought in a figure from your textbook. There's the sun in the middle, and I don't know if you can see it very well in this diagram, that there's a blue orbit of a planet that marks Neptune, and then kind of in the plane of the ecliptic beyond Neptune begins a region that we call the Kuiper Belt. So Kuiper Belt objects or Kuiper Belt comets kind of come from there. The Oort cloud, I hope you can kind of see, the Oort cloud is actually, again, rocky, icy material, but the stuff in the Oort cloud, and we'll talk more about this in coming up in this course, but stuff in the Oort cloud is actually very much farther away than the Kuiper Belt. All right. Then on to next page. So I went ahead and snagged a figure from the internet to kind of show you tectonics. So in order for you to understand tectonics or kind of pull tectonics together, you've been exposed to it, I'm sure, in high school earth science. But basically, we have a lithosphere. The crust is the upper part of the lithosphere that's actually moving on liquid mantle. Okay, and these slabs of lithosphere are moving via convection. So I kind of have three terms there, kind of all balled up into tectonics or plate tectonics. So then to kind of describe it on this figure, we have the warm core, okay, and what the core does is create these convection cells. Okay, so the liquid mantle closest to the core is heated up, it expands and it rises. It cools down as it gets farther from the hot core. Okay, it kind of cycles down, kind of hugs up against the lithosphere, and then it sinks down to complete the sail. two cells. Okay, so the lithosphere plates then are moving. So actually, we can kind of consider. Go back. Let's see. Can I go back? Oh, that isn't what I wanted. That isn't what I wanted. All right. But what I wanted to emphasize is that with tectonics, we can have plates diverging and plates converging. And so actually it's both kind of shown here. In the middle, there are plates diverging, and on the edges, plates are converging. All right, the next term is, or actually before I went to the next term, planetary differentiation, I just brought in a figure from your textbook to try to emphasize the figure where the gray is the core. Don't worry, but actually there is an inner core and an outer core. Just know that that gray part is the core. And then the kind of the dark orange around that, of course, is the mantle. We have an upper part of the mantle that is solid and associated with the crust to make the lithosphere, and then the inner part of the mantle is ooey gooey and is important for convection and movement of plates. Then go on to planetary differentiation. So early on in the history of our terrestrial planets, because this chapter was all about terrestrial planets, the terrestrial planets were still fluid, and so that allowed for heavier material within that budding planet to sink and lighter material to rise. We call this planetary differentiation. Surface erosion. Your text, or in this chapter, we talked about kind of four different, 4, 5, 6, I don't know, ways that our planet and planets in general, if they have these mechanisms, can kind of resurface themselves. Volcanism, tectonics, wind, water, debris, and ice. Okay. The next one, Mercury's cliffs. We think that they formed as Mercury cooled. Well, they're called scarps. I like that word. Caloris basins, simply know, I think will suffice that Caloris basin is also on Mercury, and it's an impact region on Mercury, and it's got kind of this cool region on the opposite side of the Caloris basin. Valles Marineris, sounds like a spaghetti sauce, is associated with the planet Mars, and I call it the big boo-boo kind of around the equator region. It's about in length, about the width of North America. Mapping of Venus, and I know I didn't include this in my lecture notes this semester, so it'll be an extra credit point, but I think it's going to be worth 1 point. Mapping of Venus occurred through the dense clouds via a satellite, basically, using echo and radar. So, yeah, that when I say mapping of Venus's surface, I mean to get the topography, because we know that Venus, as it turns out, has these kind of volcanoes that appear to be kind of maybe dormant right now. And also Venus has craters, but not as many craters as Mercury and our moon. And Venus also kind of has some fracture marks. So, greenhouse gases. Whatever these gases are surrounding, that they are functional at trapping thermal energy, interacting with thermal energy. So they make it so a planet that maybe wants to cool down will not cool down. Greenhouse gases include carbon dioxide, water vapor, methane, nitrogen, and oxygen. So how did Mars lose its atmosphere? So what I did was kind of here on the review sheet, kind of broke it up into 3 steps. First, Mars cooled quickly because it's smaller than the Earth. And as it cooled or solidified internally, it lost its magnetic field. And the loss of this magnetic field then allowed it to be susceptible to the sun's solar wind. So the solar wind basically took Martian atmosphere and headed it down the road. Okay. Flowing water. Earth has it currently, current water, and the Mars has had flowing water in the past. We can tell that by erosion marks on the surface of Mars. Pretty exciting. Phobos and Deimos, I think, is going to be another extra credit point because I'm not sure I emphasized it written-wise anyway in my lecture notes. But Phobos and Deimos, can you see them right there? Not drawn to scale, relatively speaking, but they are moons that orbit the planet Mars. Again, extra credit because I don't think it made it to my my lecture notes, but Mars is red because actually the element iron has reacted with oxygen to form iron oxide. So is that not cool or what? The last topic there, magnetosphere and magnetic field, actually they mean the same thing. So I kind of brought in the figure of the Earth's that your book has for the Earth's magnetic field, and then I said two conditions in order for a planet to have a magnetic field is it needs to, near the core, have fluid near the core. And the thing about, for instance, Mercury is it's so small it has no fluid near the core. Similar, maybe we think with Mars, the Moon doesn't have any sort of fluid near the core to create a magnetic field. The other thing is that that planet needs to be spinning on its axis sufficiently fast in order to create the moving charged particles that create the magnetic field. So those two conditions need to be met in order for a planet to have a magnetosphere or magnetic field. So with regard to which planets in this chapter have magnetic fields, the Earth has a strong magnetic field, and I put Mars, we think, still has a wimpy magnetic field. I'm pretty sure. But actually, in the next chapter, when we talk about the gaseous planets, I want to say all of them meet these two criteria to have a magnetosphere. So the giant gaseous planets do have magnetic fields. Speaking of the next chapter, it's funny because when I got to chapter 8, I'm like, wow, there's not very many terms there. So kick back and enjoy those gaseous giants. So one of the things I want you to keep in mind is that Jupiter, Saturn, Uranus, and Neptune all have rings, although we think of Saturn as beautiful rings, but they all have rings, and they all have an assortment of moons that orbit them. The next topic there is to compare the densities of Jupiter and Saturn. And so that first little picture up there from your textbook is showing you that Jupiter is more dense than Saturn. Actually, Saturn is so low in its density it would float on water. I just think that is so cool. And then you need to know kind of, or be able to kind of tell me why that is. And the pillows say it all, right? So basically, if you compare Jupiter and Saturn, one of the things we know about Jupiter is it has more stuff. It has more hydrogen and helium gas associated with it. And so just like a pile of pillows, okay, even though hydrogen and helium is very fluffy, just like pillows are, if you get enough pillows, it is going to squish the pillow at the bottom, basically. Okay, so there's that. The next question was about one of the Galilean moons around Jupiter. It actually is kind of the pockmarked one that has, it's spewing sulfur-containing compounds as associated with its volcanic activity. But with volcanic activity, it needs to have some sort of fluid in it. Why is it so ooey gooey and or gassy? Why is it warm, basically? And we know that Io maintains its heat because, and I see it's written kind of in brown up here next to the figure from your textbook, is because when Io, when Io is near Jupiter, it kind of is elongated near Jupiter. When some of its fellow Galilean moons, shown here, Europa and Ganymede, when they come close to Io, Io is kind of attracted towards them. So poor Io, it's kind of like a flex ball or stress ball. If you ever kind of take a stress ball and kind of squeeze it, squeeze it, release it, that's Io. And one of the things you notice about your stress ball is it gets hot. And so that's what Io is experiencing. Saturn's rings. Okay, actually Saturn's rings are individual particles, and what makes them so reflective is because they're icy coated rocks. So what gives Uranus and Neptune their blue color? Methane, CH4. Triton simply is a moon that orbits Neptune, and there's some other cool things about Triton. Remember, it's that one that has kind of cantaloupe surface, but Triton is a moon that orbits Neptune, and I want you to try to kind of keep it separated from the other moon, or another moon of interest, Titan. And actually Titan is that cool moon with an atmosphere that orbits Saturn. The Galilean moons, I went ahead and brought in a figure from your textbook. And let me go back a little bit. So, okay, there, that's what I wanted. The figure from your textbook that that shows the 4 Galilean moons. Don't think this is to size. Okay, we have Io, Europa, Ganymede, and Callisto. So you might want to jot those down, Galilean moons. And then related to icy Galilean moons like Europa and maybe Ganymede, and I don't think Callisto, we scientists know that there's actually tectonic activity on those moons, those icy moons. Okay, and so this is actually kind of showing you how the icy moons would have tectonic activity, plate tectonics. And it has to do with the fact that underneath their icy crust, there's actually liquid water, not liquid mantle, liquid water. And that liquid water, there are convection currents, convection cells within that liquid water, because the cores of those moons are kind of warm, like the cores of like the Earth's planet that creates the convection cells that moves our lithosphere. So you might want to, hint, hint, be able to kind of talk about tectonics here on icy moons compared to tectonics on terrestrial planets.